Okay. So, as you know, this week there won't be any labs. So you get this week off in terms of doing the lab. Uh, the lab, the lab three simulating is due this week. All right, that's going to be due on Thursday. Uh, I think everybody seemed to be doing okay there. I haven't gotten any questions on those. Maybe there's one person that I haven't got a chance to reply yet. And then next week we'll do labs again when I'm back in the office. Okay. And I will be posting the next homework uh, probably after today's lecture. I will post the mechanical homework. So let's go ahead and jump into the mechanical presentation. Module number 4. So I think we saw some of these slides last time already. So just a recap here. Uh, the mechanical systems are very similar to electrical systems that we went over the past couple of lectures. So instead of seeing resistor, capacitor, uh, voltage and current, and conductor, a mechanical system would have the corresponding elements, such as a spring here, such as mass. Look here, you got three masses, and then there's friction. Okay, that's known as Fe1. So these here, the whole idea is, okay, how do you derive a transfer function on a system like this? Okay, let me admit some of the folks that are waiting. Um, it's kind of annoying that Teams require you to admit attendees and not automatically admit them. Maybe I just need to do some settings. Okay. So of course, we looked at a mechanical system like this radar system, where the corresponding simplified schematic is like this. Here's the electrical part of it. The controller, the amplifier. Here's the motor system with the armature and the torque and the angle, and here's the load, inertia, and dampening coefficient. Uh, this is the dish itself. Okay, and so the motor has this kind of transfer function that we talked about, and the load has this kind of transfer function that we talked about. So the idea is, okay, so if you give numerical parameters of inertia, torque constant of the motor, etc., how do you come up with numerical values for the A, B, omega n, and zeta? Okay, that's going to be the goal for the next couple of lectures. We looked at this drive, and very similarly, its transfer function are a cascade of the motor, right? And there's a computational relay, and these are resonances. So if you combine all these guys together in terms of product, then you get a high order transfer function that represent the actuator system here, servo system. Okay, and some of these parameters of A and B and zeta again are given below here. So if you really want to simulate the disk drive servo, really, these can be used as numerical coefficients in this model, and you can see how it behaves, especially how the resonance impact the system. And here's the signature. Here's the Bode plot for the frequency response of the disk drive servo system, where you got these here being resonance. So here's the resonance of the arm, and here's the resonance of the suspension. So the arm is this part here, okay, and the suspension is this thin, very thin, light, flexible piece down here, okay. So therefore, it's lighter, thinner. That's why it's higher frequency resonance. Okay, so now we get into into the technical stuff. Okay, so if you've already taken statics, then this would be pretty easy review. And if you haven't or you don't plan to, I know the CPE students are not required to take statics anymore. Actually, that's true with double E as well, but that's only recently. So then I'm going to assume that you don't have any background on static and walk you through some of the basic relationships. Okay, so the first basic mechanical component is a spring. Uh, okay, and of course you know a spring, when you push it, you require force to compress the spring. And when you compress the spring, there's going to be a reactive force that will try to push it back out. But when you pull on the spring, there's going to be a reactive force that you're going to try to pull the spring back into its equilibrium position. Okay, so the relationship between force, that means the force exerted on the spring, is equal to the spring constant, that's called K, times the position of the spring. So position of the spring is, say you pick like maybe here the midpoint here. This is X is the position, right? That's where X is 0. Okay, so if you want X to be larger, meaning that you want to pull the spring out further and further so that that displacement is larger, then the force required to pull the spring out that far away is going to be proportional to how big the spring is, or the spring constant. So this relationship should be pretty intuitive. Okay, the more you want to compress or the more you want to stretch a spring, displacement wise, then the more force, the proportional amount of force is going to be required. Okay, and the next element of a mechanical system is the friction, or what's called on here viscous damper, and it's shown by this symbol here. Okay, whenever you see the symbol, think of it as friction. And by the wall here is basically just a stationary platform where these are connected to, just so that you have some stationary reference point. Okay. The relationship between force and in this case the velocity of the position of the mass, if you will, is going to be Fv, which is the friction coefficient, times the velocity. Okay, so the think of a mass sitting on a floor with friction. So the faster you want it to go, then the force that you apply to it have to be proportional to the speed that you want it to go. Okay, so therefore the relationship is force is equal to coefficient, the damping coefficient or friction coefficient times the velocity, or conveniently in the Laplace domain, it's F of V times S. Okay, is the impedance, if you will, is the relationship between X and big F. And last but not least is the mass. So a lot of you should remember this from physics. F equals ma squared. No, sorry. F is equal to ma. Or in other words, the force exerted on is equal to the acceleration times the mass. This is ma. Okay. So written in terms of the position, then F is equal to the mass times the double derivative of the displacement. So therefore, in the Laplace domain, the big F is equal to ms squared times big X. Okay. So these are very basic. Whenever you see these components in the schematic, basically you just apply these individual rules or properties of these elements to derive the dynamic equation that leads to the transfer function. Any questions so far? Question? Feel free to interrupt me if you have a question, okay? Otherwise, we'll continue. Okay, so we're going to look at a very rudimentary mechanical system. So think of this as maybe like an RLC, a simple RLC circuit, if you will. Okay. So a mechanical system, always have a mass, and it always have some spring constant. Even though some system may look very stiff, but there's spring constant in there, that it may not be a large value, but it's there. Whereas other mechanical system where it's really flimsy, then the spring constant is going to be higher to reflect that flimsiness. And then, of course, every mechanical system has the dampening or friction. Okay, and all these mechanical systems usually sit on some kind of platform or tied to some kind of platform. Hence, we got this. Okay, so it's in our interest to figure out what is the transfer function of a system like this, where the input is the force, okay, exerted on the mass, and the output is the displacement, meaning the displacement of the mass. Okay, so the way that you determine the, I guess, differential equation, first, the differential equation of a system like this is you draw a free body diagram. Okay? A free body diagram basically starts with the point where you define the displacement variable, like x. Okay, if you define x to be the displacement of the mass, then you draw the mass here and you say x here, right here. Right here is what x is 0, and x gets larger as the mass moves toward that direction. Okay, or x get negative number-wise larger as if the mass moves toward the left. Okay, so the free body diagram calls for the basic rule where the sum of all the forces acting on the mass should be 0. That's Newton's law. Okay, so this is where we go into each element connected to the mass and figure out, well, what is the force exerted on it. Okay, so the input force is pretty straightforward. That's F of t. Okay, that's one force acting on the mass. The second force acting on the mass is caused by the spring. So here, what you want to imagine is, if as x gets positive, in the positive direction, as x gets larger, what kind of force will be exerted on this mass caused by the spring? Well, if x get larger, that means that this mass is pulled toward the right, which means you're expanding the spring, you're stretching the spring. Okay, so when you look at this picture and when you see the spring is stretched, then you can intuitively see that the force acting on the mass would be the spring trying to pull the mass back toward its equilibrium position. So therefore, the mass experiences the force kxt, okay, toward the left position, direction. Okay, so that's that. And the next one, the friction Fe here. So think friction. Friction force is always in the opposite direction of a conventional displacement. So here, again, if you define displacement to be positive in that direction, so if the mass moves in that direction, then the force caused by the friction is going to be against that, which is going to be the other direction. That's why this force vector here is Fv times dx dt. So now we got 33 attendees. That's looking a little better. Once again, glad you're all able to make it online today. Good job. Okay, and then lastly, and you remember from physics, F equals ma, which means that, imagine if you push on a car, right? If you stand on the ground, you push on the car, you're going to feel the force of the car pushing back toward you. Okay, and that force that is against you against the direction that you're moving, trying to move, is going to be ma, or m d squared x dt squared. Okay, so here we define the positive direction of the mass to be toward the right, then the ma force is going to be opposite of that, which is, that's why this vector is toward the left. Okay, so at this point, this free body diagram here has captured all the forces that are acting on this mass, where the displacement is defined to be x of t, and when the mass is stationary, that's when x is 0. Okay, so this here is called the free body diagram. So now applying Newton's law, where all force acting on a stationary mass is 0, basically you add all these forces together, or you put all the forces in one direction is equal to all the forces in the other direction. So all the forces going to the right, which is just f of t, is equal to all the forces going toward the left, which is, the m d squared x dt squared, f v dx dt, and k x of t. Okay, so this is a differential equation of this schematic. So to get to the transfer function, you just take the Laplace of this, and the Laplace of this will be ms squared big X plus fvs x plus kx equals big F. And so if you put it in the ratio of output x over input f, then it is 1 over ms squared plus fds plus k. Okay, so this rudimentary common mechanical module here has this transfer function. So whenever you see something like this, you can jump to this formula here and say, okay, just plug in the mass, friction, and the spring constant to get your transfer function. It's as simple as that. Any questions so far? It's funny, you guys got so many questions when we're live in class, but online it's like everybody's quiet. Strange, isn't it? But think about it. Engaging online is so useful to master, because you know that most people, your peers, tend to. It's very easy to keep low key and not participate online because the fact that it's online, nobody can see you. There's no eye contact or anything like that. So staying quiet is pretty easy. But speaking up and engaging online is actually the next level of communication that I would encourage you to practice. I'm not trying to bribe you into engaging online, believe, but just pointing out that it is something very common that when you have
Yes, sir. I did
online
have a
meetings
from earlier.
Oh, okay, there you go. I bribed somebody to.
I was raising my
participate.
hand. I don't know if that works or not, but
Oh,
was
okay.
yeah, in this class, in terms of our mechanical transfer functions, are we only going to be looking at spring mass dampener systems, or are they going to be more complex?
Well, good question. Was that Osama?
It was me, Osama,
speaking?
yes, sir.
Okay, yeah, Osama. We will look at. So what we just looked at basically is called the translational, meaning mechanical system that moves on linearly. Okay, that kind of mechanical system. After this, we're going to look at mechanical system where it's rotational, where there's torque, angular displacement, inertia, and things like that. Very similar to translational, but it is a different category. And then after that, we're going to look at electromechanical, which is where we combine motor with rotational and even translational mechanical system to make up a complete motorized electromechanical, where we will derive transfer functions and develop control scheme and things like that. So to that extent, that's what we're going to cover in terms of mechanical system.
Okay, thank you.
Okay. All right. Anybody else? Yeah, when I'm screen sharing, when I'm going through the slides, I might not see the chat or the hand raise. So it's okay if you just interrupt me and speak up if you need to insert a question or comment. Okay, don't mind at all. In fact, I think that's useful and healthy communication. Okay, so uh, here's an example of a 2 degrees of freedom. So 2 degrees of freedom, that means that there's two state equations or two differential equations. Think of this like a circuit with two loops that you have to derive the two current and voltage equations. Same thing here. Mechanical system, especially when you have two masses that are linked together through springs and friction and so on, then you know that there's going to be two state equations that you need to work at. Okay, so let's see if we can go through here and figure out what are the or how to come up with the state equations for this system. Okay, so again, usually the most obvious is where you go to the masses, the mass element, and designate a displacement state variable. Like M1 here, let's call, okay, the displacement of that is X1, and M2 here is X2. Okay, so now you try to draw the free body diagram of M1 and M2 and figure out what all the forces acting on each of the mass. All right, so starting with M1, so here's the free body diagram. So M1, you see that, so first of all, this system, you don't have an external force. Okay, so that's absent, that's fine. Because that could easily be a force maybe acting on M1 or force acting on M2, or maybe there's two forces. But to keep this problem simple, there isn't any external forces. So therefore, when you look at the free body diagram of M1 here, you ask the question, okay, what are all the forces acting on M1? If there was a motion of the M1 toward the positive direction. Okay, so you first of all, okay, well, there's a spring that's tied to M1 here. So if M1 moves toward the right, then this spring is going to be stretched, right? Which means that it's going to try to pull M1 back to the left. So therefore, you see that this spring here is that the force here is going to be toward the left. It's going to be the value of K1 X1. Now, why is it negative? I wonder if this example uses a different convention. Okay. Okay, this example might be confusing because it moves the mass toward the left rather than to the right. Let's hold off on this example for now. Let me pick another example that. Okay. This is a car suspension example. Okay, hold on. Let me do some fishing with my old notes to have some simpler numerical examples. So hold on here. Bear with me for a few minutes. I'm still looking Yeah. Huh. Okay, hold on. Windows loading file, it's kind of slow. We see some retrieve file with my notes on some additional example, but it's from archive. Loading slowly. Okay, let's see here. I'm gonna grab a cup of coffee if you want. Probably another minute or so, because it's archived, so it's taking a little bit of time to retrieve the files. Sure. Hmm. Okay, I have an example here. See this back on share mode. Okay, so let's take a look at this example here, where you have a mass connected by a spring to the wall, connected to a spring through another mass, but it's really zero value. And then you have that's connected to another spring and a damper, and here's friction. So this is basically a system, a 2 degrees of freedom that we want to derive the transfer function. Okay, so the two, of course, you have the number of displacement states will have the same number of free body diagrams. So here we define this mass here is to have one displacement state, let's call x1. And this point here, which whenever you have another point that moves asynchronous uh, to an already defined displacement state, then we define this to be the next state variable. So here would be x2 displacement. So this system has x1 and x2 as your displacement, and then there's a force uh, exerted on this first mass over here. And so let's see if we can try to come up with the state equation. Okay. So the first thing you do is you draw the free body diagram. So it's starting with this mass here. So you have the mass block, and you ask yourself, well, what are the forces and what directions are the forces acting on this mass? So the first trivial one is by definition, right? This input force here is the force going to the right direction, okay, meaning the positive displacement direction. So that's there, okay. And then next one, let's go ahead and take a look at the spring constant. So as the mass moves in the positive direction, that means that the spring is going to be stretched. Therefore, the spring is going to try to pull the mass back toward it, meaning to the left. So therefore, that force is going to be K1x1 going in the left direction, like shown on here. Okay. The next force acting on this mass is the friction, which is always going to be the opposite direction of where the positive displacement is going to be. So if the positive displacement is going to be toward the right, then this friction force is going to be going to the left, where it's going to be FV1 X1 dot for the velocity. Okay, so we're taking care of the spring constant and the friction. Now, what is the force acting on this mass caused by this spring constant? So this one here is a little bit tricky. You gotta think through it a little bit. So again, you can imagine that if this state here moves further than this mass, if this point moves further than this point, which means that the spring is going to be stretched toward the right. Okay, in order for this point x2 to move further than x1, that means that is x1 minus x2. Let's see. If x1 minus x2 is a positive number, okay. Let me rewind 10 seconds. Let's suppose that if we imagine that x1 moves further than x2, okay? If x1 moves further than x2, that means that x1 minus x2 is going to be some positive number, and this spring is compressed, right? And if this spring is compressed, it's going to try to push the mass back toward the left. Okay, so therefore, the force acting on this mass by K2 is going to be x1 minus x2 times K2, and the direction is toward the left. Okay, so this is going to require kind of thinking, going through this through your head a couple of times to see the logic behind it. Okay, let me explain one more time. You can make one of two assumptions. You can say, okay, the x1 is going to move further than x2. That's one assumption. Or you can say x1 moves less than x2, which is where the spring is going to be stretched rather than compressed. Okay, so let's make the first assumption where x1 moves more than x2. That means that this spring is going to be compressed. And x1 minus x2 is going to be a positive number because x1 is bigger than x2. And if this spring is going to be compressed, then the spring is going to try to push the mass back toward the left. And so that's why the force is toward the left, and the value is going to be x1 minus x2 times K2. Okay? If you use a second assumption where x2 moves more than x1, meaning the spring is going to be stretched, and x2 minus x1 is going to be some positive number, then this force becomes x2 minus x1 times K2, but the direction is going to be to the right because the spring is stretched. And as you can see, that is exactly the same as this here, except the directions are different, which is going to be just a difference in a sign. Okay, so any question there? Anybody confused? Good. Nobody's confused. Amazing. Okay, and then the last force is, of course, the ma, force equals ma. So whenever you have a mass and motion defined, then there'll be a counter force that is ma, which is m x1 dot dot. Okay, so that completes the free body diagram for the mass on the left. That's right here. Okay, let's move to the next free body diagram, which is this point here where x2 is defined. So of course, this is just a dot, or think of it as a mass but zero value because there isn't a mass there tied to those components. So we just show it as a dot. So you ask the same questions again. What are all the forces acting on this zero mass point. So you see, okay, this spring here, K2, and using the same argument, not argument, same logic that we did to come up with this, think of this here. So imagine, I guess on here, x2 minus x1 is a positive number. That means imagine that, yeah, x2 moves more than x1, which means that uh, this is going to be stretched. Yeah, this spring is going to be stretched. Therefore, the force is going to be trying to pull this mass back toward the left. Okay, with the K2 constant. So therefore, x2 minus x1 times K2 and toward the left direction is what that force is going to be, acting on that point. Okay. And then this spring constant here, because it's tied to a stationary platform, then it's simply the force there. As x2 moves toward the right, this spring is going to be compressed. Therefore, the force is going to be to push it back toward the left with the value of K3 x2, and the direction is toward the left. Okay. And then there's friction damper here, which is always on the opposite side of the positive displacement direction, which means that it's going toward the left, FB2 x2 dot. Okay, and lastly, if this has a mass, then there will be, a force on the left direction, mx2 dot dot. But since there's no mass here, then it's going to be simply zero. Okay, so now we have this free body diagram for both nodes. Then we just write out the equation. The sum of forces toward the left is going to be the sum of forces to the right. So here, that's why you see K1x1 plus FB1x1 dot plus MX1 dot dot plus X1 minus X2 times K2 equals F. Okay, and so if you factor all that out and write it in Laplace equations, then you see the Laplace x1 times this ms squared plus fb1s plus k1 plus k2 minus k2 x2 equals big F. Okay, so that's one state equation. And then over here, you do the same. All forces on the left should be sum of all forces on the right. In this case here, they're all in the same direction, so that's why you got this equation. Okay, and then if you do the Laplace transform, you get this equation. So at this point, you have two unknown, meaning the two state variables, x1 and x2, and you have two equations. So whatever you want to know, say if you want a transfer function of x1 over f, then you solve this system of equation to solve for x1 as a function of f and the parameters. Or if you want to solve for x2 over f, then again you solve the system of equation, or solve through substitution to come up with the transfer function of x2 over f. But again, just like circuits, I don't expect you to spend a lot of time or be tested on linear algebra or system of equations just for the sake of solving equation. I'm not going to do that. However, if anything, I would expect you to be able to derive the state equations like this particular example. Okay? Any questions so far? Go back here. See that any raised hands? No. Oh, okay. Osama, you have a question.
Okay,
no,
sir, I didn't raise my hand. I don't know what that was.
Okay. I think that was the previous time you raised your hand, I think. Okay. This example let me hold off on this example because this example, there's actually a physical demo of a spring mass system that I'm gonna show you next week, next Tuesday when we're back in the classroom. I'm gonna show you the physical demo, but first I'll derive the equation to be here, and then I'll show you why the behavior of physical demo with this equation and the plot here. Okay. All right. So with that, let's go ahead and jump to the next type of system that what we call rotational system. Let's see. Should I stick to these notes? Yeah. Since we're on it, let's continue here. Okay. So we've just moved from linear translational system to more of a rotational movement, which is called rotational system. Okay, very similar, except the variables are and the terminologies are different. Okay, so you start out with again you have a spring constant, an element here, but except this time the force is a torque. Okay, because think of this as a power drill, right? You get rotational force and motion and things like that. So a torque is designated as this vector here, labeled to be equal to T for torque. And of course, this shaft, this axis also have rotational displacement that we're going to call theta. Okay, and so a spring constant in a rotational system has a relationship of torque is equal to the spring constant K times displacement. Again, think of it as a spring, and if you try to twist the spring or rotate the spring, the more displacement you want the spring to, the more displacement you want to impose on the spring, meaning that the more force you have to put in. Hold on. So torque is equal to spring constant times theta. Then next is the friction. Think of those of you that ridden have ridden roller skates or skateboard, right? The tighter the bearings means that the more friction. That means that the harder it is to build some speed on your wheel or your wheel to turn. So therefore, the torque required to establish higher velocity is going to require a proportional amount of torque, proportional by the amount of what we call D, capital D here, which is think of it as the friction coefficient. Okay, so torque is equal to D times theta dot, or D times omega. Omega is velocity, angular velocity. Okay, and then lastly, you have inertia. Inertia is what's hanging on that rotational shaft. Think of your power drill, right? If you try to turn your power drill, if you hook a big long heavy drill bit, then it's going to require more battery, more force to turn that drill bit, especially the acceleration, as opposed to a smaller load. So the bigger the load means that the bigger the inertia that is designated by the variable J, inertia. Okay, so this is like F equals ma, except it's rotational. So now its torque is equal to inertia times acceleration, angular acceleration, okay, or is equal to omega dot times J. Okay, going back to the antenna dish example, and see if I can. And this is the inertia right here, right? It's tied to a shaft, a rotational system, right? So the bigger the inertia is going to require, the more torque from the motor to turn it, versus the smaller the inertia is going to require less torque. Okay. Similarly, now we draw the free body diagram or the schematic and free body diagram and try to come up with a differential equation and the transfer function for this. So here's the schematic of a rudimentary second order rotational system. Okay, very much like the second order rudimentary system for the translational system that we looked at earlier. So you got a inertia load with some friction, some spring constant, and there's some torque exerted on this system, and there's a state angular displacement state variable called theta. Okay, so the way that you do the free body diagram of this here is you look at, think like you're holding the drill, and you look straight into the drill where the shaft is pointing to your face. So that's this dot here. Okay, all right, and so this dot here, so this shaft here has inertia sitting on it. It has some torque exerted on it, and that will create some displacement, angular displacement theta in that same direction as the exerted force. Then you're going to have the counter force due to bearing friction. That is, due to this bearing friction here, that is designated as capital D times theta dot. And then you have the again, like the force equals ma, you have J theta dot, which is always counter the direction of the positive direction that you're trying to move. Okay, so therefore you have the idea. The second Newton equation is that the sum of all torques acting on this shaft should be equal to 0. So here you see, okay, all the one that is counterclockwise is J theta dot, that one, plus D theta dot, that one, okay, plus K theta, which is this one, okay, is equal to the clockwise force, which is the input torque T. Okay, and so if you take the Laplace of this and put it in the form of output over input transfer function, output is angular displacement, input is torque, this is your transfer function. Okay, so you see that this second order transfer function, the coefficients of this transfer function are dependent on how much inertia, how much bearing friction, and how much spring constant are in the system. Okay, now think about this. If I ask you to think about, well, remember we talked about resonance a lot, right? We talked about the fact that resonance, the higher the frequency of the resonance, then the better off you are, because you can get the system to respond much higher speed before you run into the problem of the resonance. I remember the example about the car rattling. You're driving an old beat-up car. Well, if your car starts to rattle at 40 miles per hour, you're pretty much limited to 40 miles per hour and not want to go faster than that. But if your car doesn't rattle until 80 miles per hour, that means you can enjoy that whole range, okay, of driving the car and not worrying about car going unstable or breaking down or fall apart on you. Okay, so when you look at this transfer function here, you think about resonance. I want you to wonder, okay, what does is J being higher or lower correspond to your resonance being higher or lower frequency? Or the same question for D and for K, right? If D is, if there's more friction, does that mean there's less, there higher or lower frequency of the resonance?
Excuse me.
Intuitively, yes, question.
Yeah, hey, it's Will. So for the line that's J double dot plus K theta plus D theta dot, and then it goes to the second line where you see all of where it's like theta times the next expression equals T. Where's that theta come from? Because my understanding is if you had J theta double dot, that translates just into JS squared, where the theta would go way out of that term.
Okay, so maybe part of your confusion perhaps is this theta looks like this theta, whereas it used to be small f and this would be a big F where we distinguish. But the fact that the one of the issue here is theta, lowercase theta and uppercase theta, they look kind of the same. Okay, but what's meant in these two equations is that this here is a time domain equation. Okay, the second equation here is the Laplace domain equation. Okay, so think of this first term, J theta dot dot. Well, the Laplace of that is J S squared big theta of S, which is this right here.
And then you just pulled it out for every term.
Yeah, exactly. You just pull out theta of S and you just leave what's inside the bracket to be, the coefficients and the S terms.
Because there's always going to be theta of S when it comes back.
Oh yeah.
Yeah, okay.
Oh yeah.
That makes sense. Thank you.
Okay.
Thank you.
So at the end, you got theta of S over T of S equals this. Was there any more question?
Yeah,
Okay.
I'm good.
Okay. So yeah, I guess down here I was trying to draw a depiction of, you got a motor, right? You got the shaft of the motor, and you got an arm connected to the shaft of the motor. But now if you put in gear ratio, you got a motor, you got a small gear and a big gear connected to the arm. That's going to provide you some leverage and some advantages. But before we get into gears, let me jump back to the slides to see if there's anything else I need to cover on rotational system. Okay, so here's a good real world example of a rotational system where you convert a rotational motion system into a linear. So this is an elevator. If you look inside an elevator, so here's the car or the cabin of the elevator. So the elevator is actually pulled by a motor, where it's a rotational system right here. But because the way that you have the belt pulley system work here, right? The motor, so this belt here converts rotational motion to linear motion of the elevator car, right? So this has both rotational and linear. Okay, so in designing an elevator system here, you gotta worry about picking a large enough motor that can handle the load of the car, that can drive the car or the cabin, up to the max speed that you want, to some max acceleration, right? If you want to go from the first floor to the third floor in half a second, well, you need a bigger motor compared to the case where you spec it to allow it to 3 seconds to go from first to the third floor. Then you have to have a smaller motor because you don't need as much acceleration, right? So that's one real example of rotational system. Okay, so rotational system, I guess the emphasis is that, look, you have something that looks like this. Whenever you see something like this, boom. You immediately should recognize that the transfer function of that system is this. Okay, we're not going to even get into a 2 degrees of freedom rotational system. That's not going to be necessary, given what our goals are when it comes to the electromechanical system. Okay, and so recap on the linear or translational system, very similar. Whenever you see something like this, okay, boom, you jump straight to this as your transfer function. Okay, and if you understand the derivation from this to the free body diagram to the differential equation to this, that's great. At least do that once.
Thanks.
So that you see how it's done. But after that, whenever you see this, boom, you jump straight to here. Is that a question? Well, okay. The duality of that is the rotational system. When you see this, boom, this is the transfer function for that module of rotational system. Okay. All right. So now we're gonna take a rotational system and we're gonna add gears to them. And here's some basic relationship with gears. Okay, so you all have ridden a bicycle or a 10-speed before, at least once in your life. Or there may be somebody that's never ridden a bicycle, but if you haven't ridden a bicycle, you try to see if you can follow the analogy here. So this is a low gear ratio where you're pedaling this, your bike pedal is on here, and compare this to this, the torque that you produce, and this is your tire sits back here, right? So the torque that you produce on this tire in this case is going to be higher torque than this here. Okay, so when you put your bike in high gear, you're gonna
You can see your
produce.
mouse.
You can see my mouse?
I
Yes or
don't
no?
think we know.
Oh, really? So none of you can see my mouse all this time?
I can
Is
see
that
it.
true?
Now I can see it. Yeah.
I can see
okay.
it now.
So you, okay. So I just got to keep it constantly moving. I thought you were saying that you don't see it throughout the lecture, which I would worry because nobody's been saying anything. Because I've been using the mouse and pointer to these a lot. Okay. Anyway, so when you ride a 10-speed bike, you control the gear level to get different torque, but the trade-off is the speed, right? When you put it in high gear, you can climb a steeper hill, but you gotta pedal a lot to get you compromise the speed. Whereas when you're in low gear, you get more speed, but you don't get as much torque. So this is more challenging when you're in a steep slope, uphill slope. Okay. All right. So gears, let me tell you up front, gears are very essential. You find gears and belts in almost every electromechanical motion system, because gears is like an amplifier, right? You know, when you think of an amplifier, you're able to amplify a signal that is very small, microvolt level, to a signal that is in millivolts or even in volt level, and enjoy the larger amplitude and better signal to noise ratio when you're able to amplify a signal like that, right? Same thing in mechanical. You know, you can use gears to amplify the torque, right? You know, you're riding your bike on, and all of a sudden you encounter this steep uphill, and without gears, it's almost impossible for you to pedal up the hill. But now, when you put it in high gear ratio, all of a sudden you're able to trek along and up the hill. Sure, there's a trade-off in speed, but that's okay. You know, if you're willing to compromise a little bit of speed, you're able to still get your bike up the hill. All right. And so the magic here is what is the gear ratio. Okay, a gear system that, as you will find out, it amplifies the torque. It amplifies the input torque. Okay, you're pedaling your bike at, say, 10 units of force, but you produce 100 units of torque on the rear wheel to get you up the hill, for example, if you have a 10-to-1 gear ratio, right? So this diagram here on the left is what the gear ratio is all about. So you got one gear with N1 teeth, and you got a bigger gear that has N2 number of teeth. Or you can look at the radius of the small gear, call it R1, of the big gear, and it's R2. On this gear number 1, you have some angular displacement called theta 1. You have some torque. That is T1, okay, subscript 1. Whereas on this gear adjacent to it, you have because the gear, how they interact, then the angular displacement rotation of the second gear is in the opposite direction of the first gear. Therefore, it's counterclockwise, and it's labeled as theta 2. Same thing, the torque that it produces is going to be T2. Okay? So in this class, think of the small gear to be the input gear and the output gear to be the big gear. In other words, most of our application is about amplifying the torque, amplifying the input torque using gear ratio. Okay, the input torque is yes.
And this probably sound dumb, but is the radius to the base of the teeth or to all the way out to the teeth of the gear?
As long, I would say all to the circumference approximately. As long as you're consistent, then that's what it's meant.
Oh, okay. Thank you.
Yeah. Okay, so let's look at some basic equation relationship between displacement and gear ratio and so on. Okay, so the first equation here is the travel distance. Okay, when these gears turn, the radial distance should be the same. So in other words, when the first gear turns, if you look at the first gear and the amount of radial displacement that it turns, it's R1 times theta 1. Okay, that is always should be the same as the radial displacement moved by the second gear, which is R2 theta 2. So I'm trying to think, R1, what's the formula for the radius of a circle? Is that 2 pi r? Yeah. Okay. So yeah, this here is basically the radial displacement. Okay, that makes sense. Okay. And so if you put this in ratio theta 2 over theta 1, it's R1 over R2. But you see R1 and R2 ratio shares the same ratio as the number of teeth, N1 over N2. Okay? So what we're trying to say
Professor,
here is, yes, sir.
I was just, so in the diagram, it says output above gear 2, so it's R2. Would that be reversed in the bicycle example? As in, the bigger gear in the bicycle would be our input gear.
Yeah, the input gear in the bicycle would be here, and the output is here.
Okay.
So
Okay.
this is where you wait. Sorry, no. I guess it depends on how you look at, because the pedal would be here.
Well, okay.
I think I
But
misspoke. I think this
you're
is
correct.
where the pedals are. This is where your input gear is.
But would that be the output gear though, because you're changing speeds, which is changing the gear size? Because I'm thinking your
Yeah.
crank would be on the right side, because that would be a fixed. Maybe I'm wrong, but
Oh,
okay.
so who thinks the input gear where the pedal is on the right side versus, or who knows? Like, who knows which side the pedals are on? Everybody
Because I'm
know for
thinking
sure based on this.
with my bicycle, when I pedal, that is a fixed ratio, versus when I change the gear on the back end of my bicycle, I would be at like a higher gear in the top, or I would be changing
So
the left side.
you think your pedals are on the right side or on the left side?
I think they're on the right side.
Okay, so let's reason through that, see if it makes sense. So if the pedal's on the right side, that's input gear. And so
I guess
the output gear is smaller than, so this is here where you don't gain any torque. In fact, you do the supplying of most of the torque and you gain a lot of speed. Yeah, somebody said something?
I think that your analogy of the bicycle, your pedal gear is fixed, and when you change gears, you're changing the gear ratio on the output shaft on the tire itself. That's what changes the gear ratio on a
So
bicycle.
where do you think the tire is? Is it on this side
Yes,
or on the right side?
it's on the left side.
The left side?
That's the
So this is
tire
where your
side.
tire is. Or is that on the right side is your pedal.
Yes.
Okay, so if this is your pedal here and this is your tire here, then the diagram on the top should say that you supply more of the torque to gain a lot of speed. That makes sense. Yeah, you know what? I need to look at the book to see how the context of these diagrams before I further confuse you all. Okay, so ignore this. Don't worry about this. I'll clarify that next step. Okay, so good question.
Okay, thank you.
Okay, everybody good? All right. So theta 2 over theta 1 is N1 over N2. Okay, so as N2 gets larger, like I said earlier, in our application, the output gear is always going to be larger than the input gear, meaning N2 is greater than N1, which means that this ratio is going to be less than 1. Okay, so therefore the output angular displacement theta 2 is always going to be less than the angular displacement of theta 1, meaning theta 1 can turn several revolutions and theta 2 may be less than a revolution if the ratio is large enough. Okay. So now take the derivative, look at velocity. The output velocity could be would be slower than the input velocity. Okay, so theta 1 could be turning really fast, but theta 2 could be turning much slower, because of this gear ratio N1 being bigger than, N2 being bigger than N1. Okay, so this is a compromise as far as the output is concerned. When you have this kind of gear system, the output is going to be turning slow while the input gear is going to be turning fast. Some of you may be thinking, okay, so what's the benefit here where we seem to be compromising angular speed at the output? Okay, well, that's the next section, which we'll talk about on Thursday. You will see that conversely, the output torque is going to be amplified version of the input torque. So this is what you gain. What you lose is the velocity or the displacement, the angular displacement. Okay, but what you gain is the amplification of the input torque, and that's very powerful. Okay, so on Thursday we'll go through the equation and we'll see, just kind of develop an intuition of these two relationships, and then we'll see how they are applied to the overall system. Okay, any last question or comment before we end the lecture today? Okay, no one. All right, enjoy the rest of your day.